Let's take a look at Singapore A-Level 2023 H2 Math Paper 2. And in the first question, we have this. It is an inequalities question. And in part A, we are supposed to find the set of values of x such that 3 modulus of x minus 2 is less than modulus of 5 minus 2x. And the most efficient way that we can solve this inequality will be to draw the graphs of the left-hand side and the graph of the right-hand side. And using the graphing calculator, these are the two graphs that I will be getting. For this, it is going to be a graph that is something like this. Okay, this is going to be from our graphing calculator. So this is y is equal to 3 modulus of x minus 2. And again, from the calculator, if I have to draw y is equal to this, we will be getting a graph that looks something like this here and this. This will be the graph of y is equal to modulus of 5 minus 2x. So if we plan to use these two graphs to find the set of values of x such that it satisfies this inequality, we are looking out for the set of values of x such that the y coordinates of this is going to be less than the y coordinates of this. And we can see that happening between these two y coordinates. So this is when the y coordinate is less than the y coordinate of the other graph. So I'm going to press into my graphing calculator to find the coordinates of these 2 points. From the graphing calculator, this point has the coordinates of 1, 3. And from the graphing calculator, this point has a coordinate of 2.2 and 0.6. So the x coordinate of this is 1, and as for this is 2.2, and therefore my final answer will be x, which are real numbers that are going to be between 1 and 2.2. This is for part A. Let's take a look at part B, where we are given this expression x plus 25 over x squared minus 4x minus 5 plus 3, and we are supposed to express this as a single simplified fraction. Pretty simple. Let's just try to group this together by multiplying 3 with this x squared minus 4x minus 5, so that I can group this into one single expression, because now they will share a common denominator, which is this. Simplifying the numerator will be getting us 3x squared minus 11x plus 10. The denominator, I'll just let it be, and this will be the single simplified fraction that I'm simplifying the expression to. And the question says, hence, without using a calculator, we are supposed to solve this inequality. So this over x squared minus 4x minus 5 is bigger than negative 3. I'm definitely going to be making use of the previous part. Just by shifting this over to the left-hand side, we'll get an expression that is like this. So we have x plus 25 over x squared minus 4x minus 5 plus 3. This is bigger than 0. And that is how I'm going to be making use of the previous part, replacing this by what we have from the previous part, which is 3x squared minus 11x plus 10 over x squared minus 4x minus 5. This is bigger than 0. We're going to factorize both the numerator and the denominator. The numerator will be 3x minus 5 multiplied by x minus 2. The denominator will be x plus 1 multiplied by x minus 5. This is bigger than 0. So the next thing that we will do is to draw a number line that try to represent each of the numbers that are derived from the individual linear expressions. So from this, we are going to derive a negative 1. From here, 5 over 3. This is going to be 2. From here, we're going to derive a 5. And if I were to substitute a number that is bigger than 5, let's say 6, into this entire expression, I'll get a number that is positive. So I'm going to put a positive here, substituting a number that is in between here, let's say 3 into this. We're going to be getting a negative number. If I were to do likewise for the other intervals, I'm going to be getting this. And we are looking for the set of values of x such that this entire expression is bigger than 0. So it is happening here, it is happening here, and it is happening here. So my answer is going to be x is less than minus 1, or x is going to be between 5 over 3 and 2, or x is supposed to be bigger than 5. So this is for question number 1. Let's take a look at question number 2. Let's continue with question number 2. And in part A of question number 2, we are given that y is equal to ln secant x. And we are going to try to show the expression that involves d cubed y dx cubed, d squared y dx squared, and dy dx. And in order for me to carry out a few rounds of differentiation to get that expression, I think what I'm going to do in order for me to differentiate more efficiently will be to re-express this as e to the power of y is equal to secant x. At least the functions are simpler on both sides. So when I differentiate this with respect to x, it is going to be e to the power of y dy dx, and differentiating this with respect to x, we will be getting secant x tangent x. And in fact, secant x is e to the power of y, so it will be e to the power of y. Dy dx is e to the power of y tangent x. So since e to the power of y is positive, we can divide it throughout this equation, leaving me with dy dx is equal to tangent x. And I'm going to differentiate this once more so that I can get an equation that involves d squared y dx squared. So on the left hand side, when I differentiate it with respect to x, we will get d squared y dx squared. And on the right hand side, we're going to be getting a secant square x. Of course, we can try to differentiate this again to get an equation that involves d cubed y dx cubed. But if I were to be looking at what the question is trying to ask us to show, we want to involve y dy dx and d squared y dx squared as much as possible. So I want to try to avoid having too many x's in my equation. And it is actually pretty easy for me to be replacing this, because if secant x is e to the power of y, secant square x is going to be e to the power of y square, which is going to be e to the power of 2y. So let's differentiate this instead. Differentiating this with respect to x again, on the left hand side, it is going to be d cubed y dx cubed. And on the right hand side, it will be e to the power of 2y, 2, then dy dx. And e to the power of 2y is actually this. Okay, so we can actually replace it by d squared y dx squared. So this is going to be 2, this replacing it by d squared y dx squared. And then we have this, which is dy dx. This is already the equation that the question requires us to show. So this is for part A. And for part B, hence, we are going to try to obtain the Maclaurin's expansion of y in terms of x up to and including the x to the power of 4 terms, which means that we do need to have a d for y dx 4 equation, okay, or expression. So to do that, obviously, I'm going to try to differentiate this again. So differentiating this, on the left-hand side, we have a d4y dx4. On the right-hand side, I'm going to go for a product rule. I'll keep this as it is. So d squared y dx squared, and I'll differentiate this, which is going to be d squared y dx squared. Then I'm going to differentiate this, which is going to be d cubed y dx cubed. Then I'll keep this as it is, which is dy dx. So what we have is going to be 2 times of this times this will be d squared y dx square plus, I don't think I can change much for this, so I am going to leave this as just like this. So this is d4y dx4, and to get the Maclaurin's expansion for y, we will be trying to find parts of the coefficient first. So I'm going to let x be equal to 0. So when let x be equal to 0, y will be ln secant 0. Secant 0 is going to be equal to 1. So ln 1, this is going to be equal to 0. Let me find dy dx also. So substituting 0 into here, we have a tangent 0, and tangent 0 is going to be equal to 0. We will need a d squared y dx squared. d square y dx square is going to be e to the power of 2y. Y is 0, so we have a e to the power of 2 times of 0. This is equal to 1. And d cube y dx cube. d cube y dx cube is going to be 2 times of d square y dx square, which is 1. That multiplied by dy dx, which is going to be equal to 0. So this is 0. And finally, we are going to come to d4y dx 4, which is going to be 2 times of d square y dx square. So it's 2 times 1 square plus 2 times of d cube y dx cube is 0. It is going to be 0 anyway, but I'm going to just still code this. This is going to be 0 also. So this is equal to 2. So now by making use of the Maclaurin's expansion formula that is in our formula sheet, it is going to be f0, which is going to be this, plus f prime 0, which is going to be this, x plus f prime prime 0, which is this, over 2 factorial x square, f prime 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 0, which is going to be this, 0 over 3 factorial x to the power 3, and f for 0, it is going to be 2 over 4 factorial x to the power of 4, and so on. So we have y to be half x squared plus 1 over 12 x to the power of 4. So this will be the Maclaurin's expansion for part B. And for part C, we are supposed to let x be equal to 1/4 pi. And by doing so, our attempt is to find an approximation for ln 2 in terms of pi. So for what we have, I'm going to substitute into this. And let's not forget about what is y. Y is ln secant x. So if I were to substitute this into the left-hand side, it is going to be a ln, then secant 1/4 pi. It's going to be equal to 1 over 2, then 1/4 pi square plus 1 over 12, then 1/4 pi to the power of 4. So on the left-hand side here, secant pi over 4 is going to be equal to square root of 2. So this will be ln square root of 2. This, I think let me just go for an approximation so I don't need to keep writing this plus ... It is going to be 1 over 32 pi square plus 1 over 3072 pi to the power of 4. So ln square root of 2 is like ln 2 to the power of half. So we can definitely bring half forward. So it's going to be half ln 2 is going to be approximately 1 over 32 pi square plus 1 over 3072 pi to the power of 4, which means that ln 2 will be approximately, multiplying 2 across to the other side, 1 over 16 pi square plus 1 over 1536 pi to the power of 4. This is for part C, and let's just erase this to write down our part D. It is actually a very short part also for part D. According to the question, we are going to be making use of our answer in part B, which is this, to try to find an approximation for, let me write it here, for the integration from 0 all the way until 1 over 10 pi ln secant x. So if I were to be doing an approximation making use of this, then this will be approximated to integrating from 0 to 1 over 10 pi of this. Let me just transfer this there. So it's going to be integrating 1 over 2x squared plus 1 over 12x to the power of 4. And I'm going to just press this into the graphing calculator because the question says we are going to be giving our answers to 4 significant figures. So just pressing this into the calculator, we are going to be getting a 0.005219 to 4 significant figures. Okay, let's move on. Question number 3. Let's take a look at this vectors question. Okay, so for question number 3, we are given points A and B with position vectors as this. So for point A, the position vector of A is -1 to 5. And as for point B, its position vector is 1, -2, 8. And in order for us to do part A, we want to find the position vector of C. We are going to make use of this equation that is given to us. BC is equal to 2AB. So BC will be vector OC minus OB. It's going to be equal to 2. AB is going to be vector OB minus OA. So OC is going to be equal to, moving this over, it will be 3OB minus 2OA. So it's going to be 3 times of OB, 1 minus 2, 8, minus 2 times of OA minus 1, 2, 5. So this OC is going to be equal to 5 minus 10, 14. Okay, this is for 3A. And now we are given the position vector of another point. This other point is point D. So the position vector is given to us for point D as 1, 2, D. Let me write it down. So OD is 1, 2, D. And we are also given this equation. We are supposed to be in part B, find the value of this D. So for part B, I am going to first find out what is this vector AD, which is going to be OD minus OA. So it's 1, 2, D, OD minus OA, which is minus 1, 2, 5. And this is going to be equal to 2, 0, D minus 5. This is AD. And we are going to find BD. BD is going to be OD, 1, 2, D, minus OB. And that is 1 minus 2, 8. This is equal to 0 for D minus 8. And then we are going to use that equation that is given to us where the question says modulus of AD is in fact equal to the modulus of BD. So modulus of AD is going to be modulus of this, which is going to be square root of 2 square plus 0 square plus D minus 5 square. And modulus of BD is going to be modulus of this. So it's going to be square root of 0 square plus 4 square plus D minus 8 square. So if I were to square both sides, then I'll be left with whatever that is within the square root. And this is going to be a 4 plus, here we have a D square minus 10D plus 25. And this is going to be 16 plus D square minus 16D plus 64. And simplifying this, we will be getting a 6D is equal to 51. This tells us that D is going to be equal to 8.5. Okay, so this is for part B of the question. Let me write down the coordinates or the position vector of OD here, okay? Because it seems like we are still going to be using it in part C. So OD is going to be equal to a 1, 2, D, which is 8.5. Okay, so we have this. Let's take a look at C, where we are going to try to find the scalar product. We are going to use the scalar product to find the angle ADB. So if I were to just do a quick sketch for myself, ADB, we are going to try to find this angle. So if I were to use scalar product, I'm going to make use of these two vectors. So it will be vector AD, which is going to be this, 2, 0, D, which is 8.5, 8.5 minus 5. So it's going to be 2, 0, 3.5. Then AD is that, then BD. BD, we have it here, 0, 4, and then 8.5 minus 8, which is going to be 0, 4, 0.5. And let me also try to find the modulus of AD, which is going to be modulus of this vector. And according to the question, modulus of AD is going to be equal to modulus of BD. So let me also write it down here. So it's going to be modulus of this. So I can either mod this or mod this. Let me just mod this. It's going to be square root of 2 square plus 0 square plus 3.5 square. This is going to be square root of 16.25. And now let's try to do a dot product. using these two vectors, which is AD dot BD. This will be modulus of AD, modulus of BD, then cosine of the angle ADB. And we are supposed to find this angle, angle ADB. So it is going to be cosine of angle ADB will be AD dot BD divided by modulus of this and the modulus of this. So we will have a cosine angle ADB is going to be 3.5 dot 0.5 divided by this, which is going to be square root of this and the square root of this. Okay, so we have a cosine of this is equal to over 16.25, which is equal to 7 over 65. So angle ADB is going to be equal to cosine inverse of 7 over 65. Pressing this into the calculator, this is 83.8 degrees. This is for part C. Let me erase this and let's take a look at part D together. Okay, let's continue with part D. And looking at part D, I do think that part D is probably one of the more challenging questions in this year's A-level H2 Math paper. So we are going to be finding the exact position vector of this point P, where point P is the center of a circle that is going to be passing through the points A, B, D. So if I have the circle to be something that is like this, and let's say this is point A, and for example, here is point B. Point D will also be a point that lies on the circumference of this circle. And at the same time, according to what the question has briefed us in part B, we know that the distance AD is equal to the distance BD. So for me to do that, let me just try to position this so that I can at least try drawing BD and AD to be almost the same length. So we are looking at something that is like this. And point P is a point that is the center of the circle. So let's say this. Let's say here is point P. And I think what I'm going to try to do is I'm going to try to use properties of circles, properties of triangle. In fact, we have an isosceles triangle over here. And if this were to be an isosceles triangle, if I were to be drawing a line from D down perpendicularly to the base, this line will be passing through the center of the circle. Okay, and it is going to be cutting the base into two equal parts. It is a perpendicular bisector. I am going to call this point M, and this is my plan. My plan is to find the coordinates of point M, or the position vector of point M. And if I can also find the ratio of dP, PM, then I can make use of ratio theorem to find the position vector of P, because I also know the position vector of D. And because these are two equal lengths, so I can actually just find OM first. It is going to be one time of OA. I'm going to use ratio theorem plus 1 time of OB, then divided by 1 plus 1. So it's going to be half of OA, which is minus 125, then plus OB, 1 minus 28. And this is equal to, OM here, this is equal to 006.5. Okay, so this is done, and I have this. So let's try to find a way to look at this ratio so that we can apply the ratio theorem. And to do that, I think I'm going to use some angles and properties of triangles and circles. Angle, because I know this angle ADB from the previous part. In fact, I'm going to just quote something that I do believe is useful from the previous part down here. So this angle ADB, we have found in the previous part to be 83.8 degrees. But let me just quote it in its exact form first. So this is going to be 7/65. Okay, so I'm going to try to make use of this angle ADB. And I also will want to make use of two right-angled triangles. This right-angled triangle and this right-angled triangle. Okay, I am going to name this angle here theta. And I will also want to just see whether I can find a good relationship between this angle and this angle. In fact, we know that this angle here is 2 theta. Okay, because we know about the properties of circles and properties of triangle that is within the circle from our secondary school. From what we have learned in our secondary school, if we were to be looking at this angle APB, this angle APB, this angle APB is going to be equal to 2 times of angle ADB. So based on this, if we were to just divide this into half, so which is going to be this angle, this is going to be APM. Dividing this into half is going to be 2 times of this divided by 2 is going to be this angle, which is angle ADM. And this angle ADM, we have just defined it to be theta. So this is going to be equal to 2 theta. Okay, that is why I'm indicating it here, 2 theta and theta. And the reason why I'm doing this is because I am going to use the properties of right-angled triangle. For example, if I were to make use of this right-angled triangle, then we know that tangent theta is going to be opposite, which is AM, over the adjacent, which is going to be, the adjacent is going to be equal to DM. Okay, and I'm interested in this adjacent length, which means that DM here is going to be equal to AM over tangent theta. I'm going to do something similar to this triangle also, and I want to quote also this AM. So tangent 2 theta is going to be opposite, which is again AM, divided by the adjacent. The adjacent is PM. So this tells us that PM is going to be equal to AM over tangent 2 theta. Okay, and this is good because we can then try to find ratios. Let me take this over this. Okay, so if I were to do a DM over PM, DM over PM is going to be, DM is this, AM over tangent theta over PM. PM is AM over tangent 2 theta. Okay, and this was the reason why we chose these two triangles, because they share the same side, AM, AM. So this will become tangent 2 theta over tangent theta. We can actually simplify this. Tangent 2 theta, if I were to make use of what we have in our MF26, converting it into a single angle, this is going to be 2 tangent theta over 1 minus tangent square theta over, this is tangent theta. So cancelling this away, we have a 2 over 1 minus tangent square theta. And we have this. That is a good thing. And what is angle ADB? Angle ADB is going to be 2 times of theta, which means that from here, we can actually write 2 theta is equal to cosine inverse of 7/65. This tells me that cosine 2 theta is equal to 7/65. And let me quote this. So we know that cosine 2 theta is equal to 7/65. And if I were to make use of what we have learned, what we have in our formula sheet also, which is trigonometric identities, we can also rewrite this as 2 cosine square theta minus 1. This is going to be this. So cosine square theta is going to be equal to, in our case here, 36 over 65. And the reason why I want cosine square theta is because I'm actually interested in secant square theta. Secant square theta is going to be flipping this reciprocal of this, 65 over 36. And the reason why I'm interested in secant square theta because I can relate it back to tangent square. And we know that 1 plus tangent square theta is going to be equal to secant square theta. So tangent square theta is going to be 65 over 36 minus 1. So tangent square theta is going to be equal to 29 over 36. And now I can plug it back into here in order for us to find the ratio of dm over pm. And this is going to be equal to 2 over 1 minus 29 over 36 because we have just found out. Okay, tangent square theta is going to be 29 over 36. And this will be giving us a 72 over 7. Let me just try to redraw this. So if I have D here, if I have a P here, and if I have an M here. Okay, we know that dm, this has a proportion of 72 versus pm, which is going to be this, has a proportion of 7, which means that this is going to be having a proportion of 65. Okay, so from here, we can deduce that dp is to pm is going to be equal to 65 is to 7. And with this, we can then try to reference this to the origin to apply the ratio theorem to find OP. So if I were to reference all this back to the origin, that means OP is going to be equal to 65 times of OM. Let me write it down. It is going to be equal to 65 times of OM plus 7 times of OD. Okay, we are referencing it to this vector and this vector to find OP divided by 65 plus 7. So it is going to be 65 plus 7 is 72. So 1 over 72 of 65 times OM. We have found it just now. This is 0.6.5. Then plus 7 times of OD. We have it previously, which is going to be 1, 2, and 8.5 here. So this will give us OP. And this vector looks like this, 7 over 72, 7 over 36, and a 2, 4, 1 over 36. Okay, this will be position vector of P. Quite a tough question. Okay, anyway, let's move on. Let's take a look at the last one here in pure math. This question number 4. Okay, question number 4 for A. We're going to try to find the exact area between the curve C, which is given to us in the parametric form, and the x-axis and the line x is equal to 21. So what we definitely want to do is to try to do a sketch of this on our graphing calculator. So we have this. I've already planted it in. We have this. Okay, and let's make sure that we go to window and set the set of values of t that are appropriate for this parametric equation properly. So this is 1 over 5, and I'm going to go all the way to like positive infinity, but I'm going to just use 20 to simulate a big value. I'm going to draw my graph, and the graph looks like this. So it is going to be the area that is going to be between the curve, the x-axis, and x is equal to 21. It is chopped off here at 10. So let me go to window. Let me extend this to, let's say, 25 so that I can have a better idea of how the graph looks like. So we see the graph as like this. Okay, it's going to go all the way until here. So I will probably need to like look at what that is happening here also to give me a better idea of how I'm going to be calculating for the area. So let me also try to change y maximum. Let's say changing y maximum to, let's say, 40. Let's see how the graph is going to be like. Okay, now I think I have a better idea of how this graph is going to be already. I know my graph is going to be like this. Okay, and x is equal to 21 should be cutting the graph this way. I saw the graph appearing starting from here. So let me do a quick check. I'm going to press trace. and 1 over 5 to insert into t. And this is actually really here. Okay, so this point here is where the graph starts. I'm going to use a solid dot here since t can be equal to 1 over 5. And this is when x is equal to 3.08. And t here is 1 over 5. We do need to find the t at this particular point in order for us to use integration to find this area here. So to do this, I am going to let x be equal to 21 for the parametric equation that is given to us. So it is going to be this. So it will be a 2t squared plus 3. This is equal to 21. T squared, this is going to be equal to 9. So t, we are going to be picking 3 instead of -3 because according to the question, t is supposed to be bigger or equal to 1 over 5. So we are picking this, which means that at this point here, we know that t is going to be equal to 3. So to find this area, it is going to be integrating from 3.08 all the way until x is equal to 21 of y dx. And replacing as much of what we have here with t. This, if I were to replace it by t, it is going to be 1 over 5. 21, if I were to replace it by t for this particular point here, this is going to be 3. Y, according to what that is given to us by the question, is 5t minus 1. As for dx, we are given that x is equal to 2t squared plus 3, so dx dt is going to be equal to 4t. So here I am going to write this as a 4t. Okay, so we have this, and we're supposed to find the exact area of this, so we have to do the integration ourselves, integrating from 1 over 5 to 3, multiplying this in, we have a 20t squared minus 4t, and this is an easy integration. It is going to be 20t cubed over 3 minus away 2t squared from 1 over 5 all the way until 3. Substituting 3 in, it is going to be 23 to the power of 3 over 3 minus 3 square, minus away, substituting 1 over 5 in, which will be 20. This 1 over 5 cubed over 3 minus 2 times of 1 over 5 square. Pressing into my calculator, my final answer is going to be 12152 over 75. Okay, this is going to be for part A. Let me erase this and let's try out part B. So now we have another curve D. Let me just write down C first. C is when x is equal to 2t squared plus 3, y is equal to 5t minus 1, and t is bigger or equal to 1 over 5. This is for curve C. And for curve D is when x is equal to 5u and y is equal to 4 over u, and the domain is just simply u cannot be equal to 0. So for part B, we want to find the point of intersection between these two curves C and D. And we also want to show that there are no other points of intersection except this point A. So to do that, we'll just solve simultaneous equation. And I think one good way for us to be proceeding with this is to form the Cartesian equation of this and then solve it with the Cartesian equation of this. So for this, let me start with y. So for curve C, let me write it down. For curve C. Okay, if I were to start with y, which is 5t minus 1, this tells me that t is going to be equal to y plus 1 over 5. Substituting this back, so x is going to be equal to 2y plus 1 over 5 square plus 3. This, I'll call it equation number 1. This is simple. So if I were to look at curve D, this y is equal to 4 over u. So u is just simply 4 over y. Substituting into here, x is going to be 5 times of this. So it will be 5 times 4, 20. 20 over y. This, I'll call it equation number 2. And I'll just substitute these two equations. I'll match these two equations together by letting equation number 1 be equal to equation number 2. So it is going to be equal to 20 over y is equal to 2 times of y plus 1 over 5 square plus 3. Multiplying this throughout by by 25, okay? Then we will, by 25y, okay, let me do that. It is going to be 500 is equal to, if I were to expand this and manipulating it, I'll be getting a 2y to the power of 3 plus 4y squared plus 2y plus 75y. Okay, I multiply this entire equation here by 25y. 25 is obtained from here. 5 squared is going to be equal to 25. So this is going to be giving us a cubic equation in terms of y, and that is this 77y minus 500 is equal to 0. Using my calculator, I am going to get values for y as 4. And when y is equal to 4, if I were to substitute back into here, x is going to be equal to 20 over 4. This is going to be equal to 5. Therefore, we know that the coordinates of point A is going to be 5, 4. And basically, this is the only solution that I'm going to be getting from solving the pair of equations simultaneously. And that is why my explanation for the last part, let me just say it. I'll say something that is like, since there is only one solution to equation number 1 and 2, therefore there are no other points of intersection except point A. Okay, this will be my explanation. Let's continue. Let's take a look at part C. For part C, we are going to be finding out the coordinates of the points when the tangent to the curve C is going to be, the tangent to the curve C at point A is going to be meeting the curve D again the second time. So we want to find the coordinates of this second time when the tangent meets curve D again. So just now we saw C as something that is like this, right? So if I were to just have a rough, like get myself a rough idea of what is going on by doing a quick sketch, A is going to be, let's say here, so the tangent will be something that is like this, okay? So let's say this is point A, and point A is also the intersection between curve C and curve D. So I don't know how D looks like, but you know, it is going to be passing through this. And according to what the question says, the tangent is going to be cutting curve D again. So let's say, you know, D comes back up here. So this is actually going to be the coordinates of the point that I'm trying to find. So the first thing that I will try to do is definitely to try to find the equation of the tangent at point A. So to do that, I am going to find the dy dx for curve C. So to find dy dx for curve C, I will first find dx dt. dx dt is going to be equal to 40. I will find dy dt. dy dt is equal to 5, and this will help me to find dy dx. And dy dx is going to be dy dt divided by dx dt. So it will be this. And at point A, let's try to see what's going to be happening at point A. We are going to find the tangent at point A. So to find the tangent at point A, we already have the coordinates of point A, so we need the gradient, which is going to be derived from dy dx. And dy dx is now in terms of t, so we want to find t at A first. Okay, and to do that, since it's going to be on curve C or D, let me just use this. Okay, so we know that y is going to be equal to 4. And y for curve C is 5t minus 1. This is going to be equal to 4. Oh, I was saying we can use this, but I realized we can't because dy dx is in terms of t, not u. So we have to use curve C. So based on this, we will be able to find the value of t. T here is going to be equal to 1. Okay, so t here is equal to 1, which means that dy dx is going to be 5 over 4 times 1. And this will give us the equation of the tangent at point A, which is going to be y minus the way the y coordinate of point A is equal to the gradient. Gradient is 5 over 4. X minus away the x coordinate of point at point A. So we have this. And based on this, I'm going to call this equation number 3. And now I'm going to try to solve, equation number 3 is going to represent this. Okay, I'm going to solve another simultaneous equation between this and D. So it is going to be 3 and D, which is number 2. So from here, I am going to try to substitute equation number 3 into equation number 2, substituting this into here. So that will be, okay, I should be substituting equation number 2 into here. I think it is going to be easier. So let me change this. Let me substitute equation number 2 into equation number 1, which will be giving us a y minus 4 is equal to 5 over 4 of x, which is going to be 20 over y minus 5. So from here, let's multiply this throughout by y, and simplifying it a little bit, we will be getting a 4y squared plus 9y minus 100. This is equal to 0. Solving for this, we will be getting y to be equal to 4, or y to be equal to minus 25 over 4. We are going to be not using this, right? Because that is going to be the y coordinates for point A. And we are supposed to be looking for this other point of intersection. So we are going to be using this. So when y is equal to minus 25 over 4, if I were to substitute this back into here, x is going to be equal to 20 over negative 25 over 4. X is going to be equal to negative 16 over 5. So the point where the tangent is going to be intersecting the curve D again will have a coordinates of minus 16 over 5 and minus 25 over 4. And now we are done with pure math. Let's move on to take a look at how we can deal with all the statistics question in section B.